You have learned a lot in Calculus 2, whether you took Calculus 2 recently or a long time ago. Chapter 9 is about vectors in R3, and eventually the plane, and operations with such vectors, and the implications of the vectors in the equations of a line in space or plane in space, stuff like that. Now, 9.1 through 9.5 was considered to be covered completely in Cal 2 here at Tech. However, lots of students come from South Plains College, Amarillo College, lots of colleges where by the nature of the course Calculus 2, vectors in R3 are not covered. Therefore, I'd like to make an attempt to review 9.1 and 9.5 quickly with the knowledge you have now as grown-ups in the area of vectors in R3. So again, what are vectors? They are oriented segments. Not only that they are oriented segments, but we make a distinction between a vector that is fixed in the sense that his origin is fixed, we cannot move him, and a free vector who is not married to the origin, he can shift by parallelism anywhere in space, and we call that a free vector. The distinction between those vectors would be V arrow, V bar. As you remember, V bar was the free guy, free vector, which is the, actually it's an equivalence class of all vectors that can be obtained from the generic V bounded somewhere at a point by translation. So you have this kind of same magnitude for all the vectors, same magnitude, same orientation, and parallel directions, parallel lines. What have we done to such a vector? As you remember very well, we decomposed him in the standard canonical basis, which for most of you engineers and engineering majors is denoted as IJK, where IJK is an orthonormal frame in with respect to the Cartesian coordinates. So I, J, and K will be the unit vectors on the X, Y, Z axes of coordinates, Cartesian axes of coordinates. So remember always that I, J, K are orthogonal to one another. Since this is review, I'd like to attract your attention to the fact that K is I cross J. Think about it, what happens, you bring I over J, and you get K because you move up, because it's like you are turning in this direction, and the screw or the whatever's from the faucet is pointing upwards. It's like the right-hand rule. If you would do the other way around, if you do J cross I, what are you going to have? Minus K. So the properties of the cross product being antisymmetric are supposed to be known. Pay attention to the signs in all the exams that you have. What do we know about the respective products for vectors in space or in plane? If you have two vectors in their standard basis, U1i plus U2j plus U3k, where ui is a real number, and V1i plus V2j plus V3k, where vi are again real numbers. The dot product or the scalar product. Now I saw that in all your engineering and physics classes you will use this notation. Mathematicians sometimes say, no, I'm going to use angular brackets because it's a scalar product in R3, or scalar product or dot product is the same thing, and that's the standard one here, U1 V1 plus U2 V2 plus U3 V3. So what do you do to remember what you do? first component as first component plus second component times second component plus third component times third component. Okay? If you are in computer science, I saw that you use this notation. I was very happy to see that, the summation notation, but you don't have to use it in our class. Now, about the cross product of two vectors, you had the definition ijk, the first row, so what you get is going to be a vector. Here what you get is a scalar as a result. Here's what you get as a vector, as the result of the cross product of a vector. So you have u1, u2, u3, v1, v2, v3. These are all friends of yours. I'm just reminding you the lucrative definitions. Now, some people said, yes, but I'd like to see the lucrative definitions that have to do with trig as well. Okay, let's see those. You asked me to remind you what they were. I will remind you what they were. For u dot v, you get the same thing as writing magnitude u, magnitude v, and cosine of the angle between them, no matter in which direction you take it, because the cosine is the same. Cosine of phi is equal to cosine of negative phi, or theta, or whatever. How about the other one? Here's where one of you had a little bit of a misunderstanding. And I saw that happening through finals, unfortunately. This is not a scalar vector that I'm writing here. It's a vector. So what's missing? This is the scalar part. And then you have times e, where e is the unit vector of the direction of the vector. The direction of u dot v. Why I cannot use another notation, because u is already taken, but e in itself should suggest to you that you have a unit vector, length 1 vector. Okay? All right, what is the, let's review a little bit the absolute value. Well, the absolute value is a scalar. So that scalar will be magnitude of u, magnitude of v, and sine of the angle. And do you guys remember the geometric interpretation of that? The area of the parallelogram based on the two vectors. Very good, and probably u cross v is the area of the parallelogram that you would draw based on those two vectors. All right, good. Now, say goodbye vectors. You've seen them through 94, 95. What was important to remember was that these vectors were the building blocks, the foundations of the equations of the lines in space that you worked with. So what did we work with? Lines in space. Lines in space can be given in many ways. But now that you remember them, I'm going to give you the symmetric equation of a line in space. Okay, hint, this can be involved, included on the final. You are expected to know it. So that is the symmetric equation, meaning the equation of a what? Of a line in space passing through or containing the point P naught of coordinates x naught, y naught, z naught, and of direction element in the sense of a vector. Now, if I were to draw such a line, I'm going to have the line over here. I'm going to have the vector, but the point is 0 on the line. I can put this free vector because he's free. He says, I'm a free guy. I can slide any way I want. So I'm going to have Li plus Mj plus Nk. This is the blue vector. Now you don't have blue markers or blue pens, but you can still do a good job taking notes. Now somebody asked me just a week ago, saying I've started doing review already and I don't understand what the difference is between the symmetric equation of a line in space and the parametric equations of a line in space. There's no essential difference. So what do? We denote this whole animal by t, a real number. And then we erase the board. And then we write the three equations that govern. I'm going to put if and only if x, y, z satisfy the following. So I'm going to have what? X equals LT plus x0, y equals mt plus y0, n equals nt plus z0. Where, of course, we understand, we know the meaning that LMN are like what you met in physics, direction cosines, you were telling me about it, and then x0, y0, z0 is a fixed point that belongs to that line. Now, since you know a little bit more than you knew in Calculus 2 when you saw that for the first time, what is the typical notation that we use all through Cal 3, all through the chapters? The position vector of a point on the line that is related to what? So practically you have the origin here. OP0 represent the vector x0i plus y0j plus z0k. So now you have a little bit of a different understanding of what's going on. And then after, let's say, t equals 1 hour, what do? You're adding the blue vector here, right? Let's say at t equals 1, you are here. You are here at P1, so to get to P1, you have to add two vectors, right, guys? This is the addition between the blue vector and the red vector, so what you get is your resultant. So if I'm smart enough to understand my concepts are all connected, the position vector in this case will be r of t, which is, I hate angular brackets, but just because you like them, I'm going to use them, x of t, y of t, z of t, and to be consistent with the book. This is the same as xi plus yj plus zk. And what is this by the actual notations from the parametric equation? This is nothing but a certain LMN vector, that is the vector Li plus mj plus nk, written with angular brackets because I know you like that, times the time t plus the fixed vector x0, y0, z0. You can say, yeah, I thought it was a point. It is a point and a vector. You identify the point P0 with the position of the point P0 with respect to the origin. So whether you're talking about Mr. P0 being a point in space, x0, y0, z0, or you're talking about the red position vector that corresponds to it, it's practically the same up to identification. So you have something very nice, and if I asked you with the mind and the knowledge we have now, what does this mean? R prime of t equals what? It's the velocity vector. And what is that as a vector? Do the differentiation. What do we get in terms of velocity vector? Prime with respect to t. What do I get? LMN as a vector, but of course, as I hate angular notations, I will rewrite it. Li plus mj plus nk. So this is your velocity. What can you say about this type of motion? This is a... Yeah, you have a constant velocity for this motion. If somebody would ask you, you have 10 years from now, you have a boy who said, Dad, or a girl, okay, let's not be biased, who learns math, good at math, or physics, and says, what is the difference between velocity and speed? Well, most parents will say it's the same thing. Well, you're not most parents. You are educated parents. So this is, don't tell your kid about vectors, but you can show them you have an oriented segment. So make your child run around in circles and say this is the velocity vector that's always tangent to the circle that you are running on. That's a velocity. Okay, and if they ask, well, they will catch the notions of acceleration and force faster than you because they see all these cartoons. And my son was telling me the other day, he's 10, and I asked him, what the heck is that? It looked like an electromagnetic field surrounding some hero. And he said, Mom, that's the force field, of course. And I was thinking, force field? This is what I taught the other day when I was talking about flux. Double integral of f dot n plus f was the force field. So he was like talking about something very normal that you see every day. So do not underestimate your nephews, nieces, children. They will catch up on these things faster than you, which is good. Now the speed, in this case, will be what? What is the speed of this? The speed of this motion, linear motion. Square root of L squared plus M squared plus N squared, which again is different from velocity. Velocity is a vector, speed is a scalar. Velocity is a vector, speed is a scalar. In general, doesn't have to be constant, but this is a blessing because elements are given constants, and in this case, you are on cruise control. You are moving on a line, in rectilinear motion, on cruise control, driving to Amarillo at 60 miles an hour because you are afraid of the cops. And you are doing the right thing because don't mess with Texas. I've had friends who came here to visit Texas, New Mexico, go to Santa Fe, go to Carlsbad Caverns. Many of them got caught. Many of them got tickets. Right? So it's really serious. Okay, let's go further and see what we remember about planes in space, because planes in space are magic. No, planes in space are very important. Planes in space are two-dimensional objects embedded in three-dimensional ambient spaces. This is what we are talking about. But even if you lived in a four-dimensional space, five-dimensional space, n-dimensional space, in the space of your imagination, if you had this two-dimensional object, it would still be called a plane. All right, so how about planes? What is their equation? In your case, ax plus by plus cz plus d is the general equation of a plane in R3. You should not forget about it. It's going to haunt you in the final and in other exams in your life through at least 2 or 3 different exercises. Now I'm going to ask you to do a simple exercise. What is the equation of the plane normal to the given line? And this is the given line. Look at it, how beautiful. And passing through, that passes through the point, another point, x1, y1, z1 that I give you. How do you solve solution? How do you solve this quickly? You should just remember what you've learned and write that as soon as possible, because, okay, this may be a little piece of a bigger problem in your exam. Quiz A. If it's If this is normal to the line, you pick up ABC exactly from the element of the line. Remember, this was an essential piece of information. So the relationship between a line and its normal plane is that the direction of the line element gives the coefficients ABC of the plane. All right, don't forget that, because you're going to stumble right into it in the exams. LX, in the one that's coming up. And Z, is this good? No, I cannot say D and then look for D. I could, or plus D, whatever you want. But then it's more work for me. Look, I don't know, suppose I don't know who D is. I have to make the plane satisfy I make the point x1 and y1, z1 satisfy the equation of the plane, and that is more work. I can do that if I forget. If I forget the theory, I can always do that. Subtract the two lines, subtract the second out of first. I get something magic that I should have known from my previous knowledge, from a previous life. No. L times x minus x1 plus m times y minus y1 plus z times z minus z1. And I noticed that most of you, you prove me on exams, you prove me on homework, know that if you have the coefficients and you also have the point that is contained in the plane, you can go ahead and write this equation from the start. So you know very well that x1, y1, z1 satisfies your plane, is in the plane. Then you can go ahead and write it. Save time on that exam. Don't waste time. It's like a STAR test. That's a 4-hour test. No, ours is only 2 hours and a half, but still the pressure is about the same. So we have to remember these notions. We cannot survive without them. Let's move on. And one of you asked me, do I need to know by heart the formula that give a formula that will give the distance between a point in space and a line in space? No, that is not assumed. You can build up to that one. It's not so immediate. It takes about 15 minutes. That's not a problem. What you are supposed to remember, though, is the formula of a distance between a given point in plane and a point in space and a given plane in space. That was a long time ago that you knew that, but I said you should never forget it because it's similar to the formula for the distance between a point in plane and a line in plane. I'm not testing you, but I hope maybe I do. I hope that you remember how to write this as a fraction. I'm already giving you hints. What is absolute value, because it's a distance, of what? AX 0 plus AY 0 plus CZ 0 plus D, okay, good. Square root of A squared plus B squared plus C squared. Right? So it's a generalization of the formula of the in plane. If you have a point and a line that doesn't contain the point, you have a similar type of formula. Good. Let's remember the basics of conics, because I'm afraid that you forgot them from Cal 2 and from analytic or trigonometry class. What were the standard conics that were used in this class? And I would like you to never forget, well, when you are in an exam, you may be asked the area inside of an ellipse, but if you don't know the standard equation of an ellipse, that's bad. So you should, what is that? A, B are semi-axes. x squared over a squared plus y squared over b squared equals 1. Excellent. And what if I have, I'm going to draw a rectangle with these kind of semi-axes A and B. And I'm going to draw the diagonals. And I'm going to draw a branch over something that is touching, kissing at this point tangent to it, and is asymptotic to the blue asymptotes. What is this animal? The standard hyperbola. Tell me what it has. These branches. The equation is what? X squared over a squared minus y squared over b squared equals 1. If I were to draw its brother, ooh, that brother would be the conjugate, okay? And you would have to swap the signs, so plus minus, and you get the conjugate. Quadrics, okay, the parabola, I don't remind you the parabola because you'll see it everywhere. I'm going to review it when I work with some quadrics. So the review of quadrics. And I really would like you to, if you feel the need to remind yourself what quadrics are, go to the so-called gallery of quadrics. Type these magic words as keywords in Google, and it's going to send you to a beautiful website from University of Minnesota that has a gallery of quadrics where not only do you see the most important quadrics in standard forms, but you also see the cross sections that you have when you cut those quadrics with horizontal planes or other planes parallel to the planes of coordinates. So I don't know in which order to present them to you, but how about I present them to you in the order that they were most frequently used, rather than starting with, so ellipsoid, and respectively a sphere. Depends if you like football, American football or soccer. Well, let's see what the equations were. X squared over a squared plus y squared over b squared plus z squared over c squared equals 1 for the ellipsoid. If a, b, c are equal and equal to r, what is that? That's a sphere of center origin, standard sphere, in radius r. These are your friends. Don't forget about them. When you draw the ellipsoid, remember that the first line, the dotted one, is an ellipse on the other behind the board, and that is obtained as x squared over a squared plus y squared over b squared equals 1. So it's going to be a intersection with z equals 0, and similarly you can take the plane that's x equals 0 and you get this ellipse, the plane that is y equals 0 and you get this ellipse. So those are all friends of yours. Remember that all the cross sections you have, cutting with planes, the football, you have what? Ellipses. That is easy and beautiful. It's not something you need a lot of thinking about. But let's move on to some wilder guys that I'm afraid you forgot and you should not forget in any case. They are the hyperboloids. Hyperboloids, the most standard ones, the classification that we had in the classroom was based on putting everybody to the left-hand side, how many pluses, how many minuses you had. If you have plus, 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 minus, or minus, 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 plus, you have an uneven number of pluses and minuses. That was the two-sheeted hyperbola. If you had an even number of pluses and minuses, that's the one-sheeted hyperbola. So let us remember how that went. Assuming that, I love this one, this is the first one, the first kind, which is the one-sheeted hyperboloid. What is the symmetry axis? It's the surface of revolution. What axis? Of axis OZ. So I'm going to go ahead and draw that. I'm going to draw as well as I can. I cannot draw very well today. Although I had 3 cups of coffee, it doesn't matter. I'm still shaky when it comes to drawing. So in order to get the cross section, the first cross section, the red one, what do you guys do? It's an ellipse because you set z equal to 0, just as you said now. So I get the ellipse of semi-axis A and B. This is the x-axis, this is A, this is B. Well, it looks like horrible, okay, B. And that's the ellipse you get. But now you say, but wait a minute, I would like to draw the cross-section that corresponds to x equals 0, and that should be in the plane of the board. So if you set x to be 0, then you have the standard hyperbola based on semi-axis B and C. Now B, you believe me. But C, you don't believe me at all because you cannot see. So if I were to be proactive, which right now I'm not very proactive, but I'll try. I'm going to have to draw, look, I'm not bad, even if I didn't have enough coffee. So the rectangle, you see B and C here? Okay, you see the asymptote? It was not a bad guess of the asymptote. This branch of the cross-section looks like really a good branch for the asymptote. Good. And the other one, in a similar way, you can find the other cross-section, which is also a hyperbola. So your old friend, which is one-sheeted hyperboloid. He sounds like a monster. What was special about him? You had some extra credit. It's a ruled surface generated by 2 families of lines. And thanks again for the model. I will keep it for the rest of my life. You got 5 bonus points because of that. I'm just, well, this is something I will always remember. Number 2, how do I write the 2-sheeted hyperboloid if I wanted it to have the same axis of symmetry? It should be a surface of revolution consisting of 2 parts, they are disconnected, right? You have 2 sheets, 2 somethings, 2 connected components. It's not hard at all. What do I need to do? The same thing as here, just change the minus to a plus. Alrighty, x squared over a squared plus y squared over b squared minus z squared over c squared plus 1 equals 0. Great. So I can go ahead and remind you what that was. You didn't like it when you first saw it, but maybe now you like it better. This is OX, Y, Z. And I'm going to draw the 2 sheets. And I'm going to ask you eventually, because I am mean, how far apart they are. It's the surface of revolution. These 2 guys should be symmetric. Well, so when if I were to take z equals 0, I would get no solution because this is impossible. I have a sum of squares equals 0, right? It's impossible to get 0 this way. when would I get 0 on the axis of rotation? Well, axis of rotation means forget about x and y. X is 0, y is 0. Z would be how much?
C.
Plus minus C. Plus minus, very good. C, practically C. If C is positive, and minus C here. So I know how far apart they are. These two vertices, not this is minimum and the maximum over here. Now, one last question. Well, okay, no, more questions. When I were to intersect with, let's say, a Z that is bigger than C, a Z plane that is bigger than C over here, what am I going to get? No.
An ellipse.
An ellipse, excellent. An ellipse here, an ellipse there, everything is symmetric, okay. And finally, what if I take x to be 0? I'm in the plane of the board. I hide the x, I get this. What is this? A hyperbola in the plane of the board, which is yz. Y is going this way, z is going up. X doesn't exist anymore. So what kind of hyperbola is this? Do you like it? So, right, you're smart. So go ahead and multiply by negative. Who said that? Xander, you got 2 extra credit points. Minus y squared over b squared equals 1. What did he notice? What did he? He guessed my mind. I'm trying to say you have no hyperbola like that. So Xander said, I know what the witch wants. She wants these 2 branches to be the hyperbola, but that's a conjugate hyperbola. That is a conjugate hyperbola because you don't have y and z with minus between the squares and a 1. So this is the conjugate hyperbola that I'm going to draw. In what color? That's the question. It's really essential what color I'm going to use. So I'm going to use green. And this is the hyperbola we are talking about. It's a conjugate one drawn in the plane of the board. Okay. All right. So if I wanted to draw those asymptotes, they would look very ugly. And I cannot do better, but that's it. So we have reviewed the most awful quadrics. A friend of yours that you by now all of you love is Mr. Paraboloid. You have used that in all sorts of examples. I'm going to remind you what the standard one was that we used before. So paraboloids, elliptic paraboloid, circular paraboloid is just a particular case. The elliptic paraboloid that you're used to is the following. Z equals x squared over a squared plus y squared over b squared. A and B being positive if you want. They don't, in general, they are not equal. The circular paraboloid, well, you simply assume that A and B are equal. And then you put, do you want a C squared or an R squared? Let's put an R squared on top. It really doesn't matter what you're putting there. Can I draw? Hopefully, I can draw. It looks like a valley whose minimum is at the origin. I'm going to draw so that the intersection with the horizontal plane will be visible to you. And I take this z greater than 0, and then I'm going to have some sort of ellipse. Under that, there is nothing. Under the origin, there is nothing because z is going to be positive. at x equals 0, y equals 0, and passing through the origin. Very nice and sassy quadric. There is one that occurred in many examples like a nightmare, and it was based on that one. And I'm going to draw, I'm going to write it, and you draw it with the eyes of your imagination and see what that is. Because you're going to bump into it into the exam. We had all sorts of patches of that. Look at the areas of the patch, and you cannot get rid of that. It's haunting your dreams. What is this? Upside down paraboloid. What is the vertex? Where's the vertex at? 0, 0, 1. Very good. What's special about it? So assume that I would draw try to compute the normal to the surface. How would I do that? Yeah, well, it's a little bit more complicated. I would have to shift everybody in one side, decide that I have a certain increasing form, then do the gradient, do stuff like that. So don't forget about this type of quadric is an essential one. Am I missing anybody important? Yes. We live in Texas. We cannot say goodbye to the last section of the chapter 9, which is 9.7, without meeting again our friend, the saddle. Right? The saddle is, this is elliptic paraboloid, and the last very important quadric that I wanted to talk about today is the... Huh? Oh, the cone is too easy. But yeah, let's talk about the cone as well. Give me an example of the standard cone. Thank you. X squared, well, I'm going to draw it first, so that you know what I want. Unless I draw it, how would you know what to invent, what to come up with? It's not an ice cream cone, it's a double cone. So I can have a positive z and a negative z, two different sheets that are symmetric one another. Right. So how do I write that? Yes, equals. Well, would you like it to be like most of those that we see in the examples in the book, right? But it doesn't have to be like that. Of course, if it's like that, of course you realize z, set a z, set a plane and altitude, then you're going to have circle, 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 circle after circle of different radii as cross sections. Z could also be negative, except for the case of the origin where you have 0, 0, 0. Now, if you were to set x equals 0, of course you would get y equals plus minus z, which are exactly these lines, the red lines that I'm drawing in this picture. So practically this is what called a what? A circular cone. If I wanted to make it more interesting, I would put a squared and b squared, and it would be an elliptic cone. And we stayed away from that as much as we could. We brought it up now because Xander asked about it. So how about the number 4, number 5, whatever is number 4, the saddle? What was the typical equation of the hyperbolic paraboloid that I had in mind? Z equals x squared minus y squared. Very good. So I will try again and draw it. It's not so easy to draw. If I were to choose x to be 0 and draw exactly in the plane of the board, z equals minus y squared would be some coordinate line, right? This is what we call such a thing. If we fix the x to be x0, we get a coordinate line. If we fix the y to be y0, we get another coordinate line. There are two families of lines. What is z equals minus y squared drawn in this board, on the board, in this plane? It's a parabola that opens upside down. Okay, so you have something like this that you're drawing, right? And then what if y would be 0? Then you get z equals x0. So it's going to be a parabola that opens up. And I have to rotate myself and draw it on that wall. But I can't, because if I do that, I'm going to get in trouble. So I better draw it like this in perspective. And you guys should imagine what we have. So if we were to cut down with a knife, we would still get these parabolas that open down, and in those directions, these are just the highest parts of the saddle. And this, let's say, this would be the lowest part of the saddle. Where is the butt of the rider? Okay. The guy's butt is here. And his leg is following the shape of the saddle going down. That's the cowboy boot. Okay? And he is, I don't know what's the attitude of the well, it doesn't look like a cowboy hat, but anyway, I'm sorry. Looks a little bit Vietnamese. That was not the intention. So
now it's Mexican. So.
They let him be Mexican. Half of the population in this town are Mexican. So this is his leg that goes down. Okay, very good. Look, he even has a, what do you call that? That's so beautiful. In the Mexican culture, they make those embroidered by hand with many colors, belts. Like there are some special belts. Okay, depends on the area of Mexico you visit. I liked several of them, and they're so beautiful. But my favorite one is the, of course, the Riviera Maya, which is where you go to the Chichen Itza, to the touristic areas, to the sea, and eat the good food, and go to Cozumel, and forget about school for a week. Okay, that is paradise for me. But Lubbock is not bad either. If I were to choose where to live and I had money, I would live in Cozumel for the rest of my life. Okay, so this is the saddle that is oriented so that you have a parabola going in this direction, going up, a parabola going down in this direction. What is magic about a saddle point? Do you remember?
It was it's a maximum.
It's one direction is like a max, in one direction is like a mean. So when you compute that discriminant, you get negative. You get like the product between the curvatures. One curvature in one direction would be positive, the other one would be negative. So it's like getting the product of plus minus equals minus. But again, we will talk about this sometime later. You don't even have to know that. Shall we say goodbye to this? I guess it's time. And chapter 9 is now fresh in your memory. You would be ready to start chapter 10. What I want to do, without being recorded,